check, 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 check.
Dongarra, and I think if I had all the time in the world, it would take me about 15 minutes to go over all his accomplishments and so on, but he has asked me to keep it to a minimum. So anyway, Jack is a university distinguished professor in the computer science department of Tennessee. He's also a distinguished research staff member at Oak Ridge Laboratory, a Turing Fellow at Manchester University, a director of the Innovative Computing Library at the University of Tennessee. His research interests are numerical algorithms in linear algebra, parallel computing, tools and architecture, and design and implementation of mathematical software. And I think everybody here will recognize those names in which Jack had part, iStack, DINCAC, LATAC, Netlib, PBM, NPI, Atlas. He's really made significant contributions. He received the first IEEE Medal of Excellence in Scalable Computing in 2008. He's a fellow of AAA, S, ACM, IEEE, SIAM, a member of the National Academy of Engineering. And the last couple of things, the last achievement I'd like to mention is something we found out yesterday, and that is that he told us that if you take all the hours of the week, 7 times a week, you just compute how many hours, and you compute how many miles he travels, then he travels at the speed of 20 miles per hour. So that's not too bad. And let's see if anybody here can match this or compute it.
Okay, well, thank you very much for the very kind introduction. So I'd like to keep this informal as we can. So if you have a question during the talk, you should ask the question, and I'll try to answer it to make it more entertaining for you as well as for me. As mentioned, I'm at the University of Tennessee, Oak Ridge National Lab, and I have a position in Manchester. So Tennessee is located in Knoxville. Oak Ridge is about 30 miles away, and Manchester is 2,000 miles away. So it makes the commute sort of interesting. What I'd like to do is to talk about what I think are 5 very important aspects when trying to use high-performance systems, and really trying to use them at scale. Right? So we'll take a look at high-performance systems in a moment, but here are the 5 things which I think are sort of critical in today's computing environment. The first one involves the effective use of many-core and hybrid architectures. So for the future, high-performance computing will predominate or focus on the use of multi-core and hybrid systems. And I'll be more specific about hybrid. Multi-core is going way beyond 2Zs and 4Zs, right? This is going to be large numbers of cores within a computing socket, and trying to effectively, this is going to be the next shot. Thanks. And to effectively use them, we have to change the way we think of programming. And I'll give some examples of that, but things have to be more dynamic. more asynchronous, and we have to organize the data so that, is that better? There's a little feedback, but it's okay. The second thing is trying to exploit mixed precision in our computations. Today, in our commodity processors, there's a factor of 2 with respect to 64 and 32-bit floating point arithmetic, factor of 2 in performance. And if we take a look at accelerators, there's a factor of 10 between single and double precision. So we would like to try to leverage that. Develop algorithms that work perhaps in short precision, try to get an approximation, and then use that approximation to enhance the precision, getting up to perhaps full precision. And that can be a big performance boost. We have to look at algorithms and software that can adapt to the environment that they're going to run on. So we think about self-tuning software that can adjust themselves to the properties of the hardware that's there. Adjust themselves to the cache size is one simple example, to the number of cores that are available, and do that in a way which doesn't involve the user having to get involved in that process. It's a very complicated situation, especially when we look at performance, and embedding that in the software is really the way to go. We have to look at fault-tolerant methods. So today's high-performance systems have on the order of 100,000 cores, and we see that number going up. The projection will be to roughly 100 million threads of execution within the next 8 years. And when you encounter that number, things are going to fail. It's going to be just a matter of time before things will fail. Today's model for computing says if a process fails, the application falls over. And we can't have that with that number. We'll be failing every few minutes. So that has to be embedded in the hardware and has to allow the software to recover from it in a very graceful way. Today's model for recovery is doing a checkpoint and restart. Today's systems don't have any disks to checkpoint to. It takes too long to move the data off to that auxiliary storage. And the final thing is about developing algorithms that minimize communication. So we have a few algorithms which we're looking at today, which we can provably say something about the communication that occurs within them. And it also involves overlapping, trying to facilitate the overlap of computation and communication whenever possible. I'm not going to have time to talk about all those things, but I would say those are the 5 key things that we're focusing on in terms of developing software. What I'd like to do first is to look at high-performance computing and set the stage in terms of where things have been and where things are going in the future. And we're going to do that through the eyes of some data that we've collected. And the data is called the top 500. Think of it like this. Every 6 months, we go out and look at all the computers in the world. Okay, well, sort of. And we rank them. Okay, we rank those computers according to their rate of execution, to their speed. And this is done by Hans Moyer, Horst Simon, and Eric Strohmeyer and myself. So we rate these machines according to some benchmark. And we can argue if this is a good or a bad benchmark. I don't want to have that argument right now. We could do that later. But for better or worse, this is the benchmark that we use. It's called the LINPACK benchmark. LINPACK benchmark solves a dense matrix problem. AX equals B. Okay, you want to solve that problem on your system, and you want to solve the largest problem you can. So typically what happens, if you increase the size of the matrix problem, the rate of execution rises until you get to some asymptotic point. We want to capture the asymptotic point for your machine. And the rules for this benchmark say you have to use an implementation or a method that does LU decomposition with partial pivoting. Right? You can't use a Strassen method. You can't use an iterative method. You can't guess the solution. Right? And we prescribe the matrix. That is, we give you the matrix, and we give you the mechanism for checking the results. So you have to get the residual correct to double precision, 64-bit floating point accuracy. So we update this list twice a year, and if it's going to be updated in 2 weeks at a meeting in Portland, at the supercomputing meeting in Portland. So the data I have today is not from that meeting because it's secret. The data I have is from the last data I have is from the June meeting, which was held in Germany. Okay, so this is a snapshot of high-performance computing. This is a snapshot of high-performance computing in terms of the rates of execution. So the way to read this is, this green line here is charting the machine that's the fastest at any given period. That's machine number 1, okay, machine number 1. And it's today at 1.1 petaflops, 1.1 times 10 to the 15 floating point operations. And by a floating point operation, I mean an add or a multiply, 64-bit operands. So that's the execution rate that they achieved for the benchmark. So they solved the linear system, and they achieved 1.1 petaflops. And this is the guy that just made it on the list. He was number 500, right? So today, that's at 17 teraflops of computing just to make it on the list. And the green thing here is the sum of the 500 machines. So that's an artificial number, right? So that's an Excel sheet computation. You sum up the 500 machines, and today we get 23 petaflops is the sum. So you can see where things have been and how things have changed over time. So notice that this is more or less a straight line here. The guy at the bottom, the sum looks like a straight line, and here we have this jaggedness associated with it as we get, a new machine comes in, which is much more powerful than the previous guy, and the performance jumps up quite a bit. What else can we talk about here? The slope of the line. So we know something about Moore's law. So something is doubling every 18 or 24 months, right? Something's doubling. So the slope of the line, we might think, is going to double every 18 or 24. So the slope of the line is doubling every 14 months. So why would it be 14 months? Well, it's the use of parallel processing, right? Moore's law talks something about the number of gates on a chip, and we loosely interpret that in terms of performance. But every time every time the list comes out, we see more and more processors in the machines, and we'll take a look at that in a moment. We take a look at the. So this is a stunning thing. Exponentials are stunning things. The guy at the bottom of the list here, that was equal to the sum of all the machines not too long ago, right? So back here in 1996, that's the sum of all the machines. The guy that just made it on the list. The other thing to recognize about high-performance systems, it takes about 6 to 8 years for a machine going from number 1 to falling off the list, right? Something that we would consider scrap metal at that point, not being worth it. And the guy at the top of the list is about $100 million. That's sort of the going price for number 1 on the list today. And this is a stunning thing. I have a laptop and I can run the benchmark. It's a dual-core processor. And when I run the benchmark on my laptop, I get a few gigaflops. That's an incredible thing. A few gigaflops. A few years ago, that would have been on the top 500 list. So back in 1995, that would have made it on the list. If you told me in 1995 you're going to have a device that you use on your lap on an airplane that runs at a few gigaflops, that would have been a joke, right? That would have been incredible. So I really have a hard time with these exponentials when it touches the things that I use on almost a daily basis, right? This is a machine I use to read my email basically, and write papers occasionally. So it's an incredible device. Okay, so let me just talk about this story here. Gordon Bell. Some of you know Gordon Bell. Gordon Bell is this legendary guy in computing. He was the architect for the VAX, the Digital's VAX and PDP series systems. And today he works for Microsoft. And he's gotten wealthy over the years from a number of things he's done. And a few years ago, he put up some of his own money. He gave $100,000 of his money to endow a prize. And the prize was in recognition of outstanding achievements in high-performance computing applications and to encourage the development of parallel processing. Right? So he gives away some money every year. And in 1988, the winner of that prize went to an application that was doing static finite element analysis. They were building aircraft. So Boeing and a bunch of other guys got together. They used a Cray YMP, and they achieved a gigaflop in 1988 for that application. So this is not a linear algebra benchmark. This is a more complicated application achieving a gigaflop of performance. So in 1998, the winner of the Bell Prize was for a high temperature superconductivity model, and that application ran on a Cray T3E with 1,000 processors, 2 orders of magnitude more in terms of processors, at a teraflop. And last year, the application that won the prize came in at a petaflop. So the application was running at a petaflop. It was running on another Cray system, seems to be a trend here, and on the order of 150,000 processors, right? So this is a big application running on 150,000 processors, doing, again, a high temperature superconductivity. So, looking at this trend here, I've got to believe that, in 2018, we're going to have a machine that's going to be at an exaflop, right? So 10 to the 18 floating point operations. And looking at on the order of 10 to the 7 processors with perhaps 1 billion threads of execution inside of it, right? Now, in some sense, that seems like a joke. How could that machine be built? How can they use that machine? But, looking at the trends, I've got to believe that it's going to be there. I'm not sure who's going to make the machine, but maybe Cray. Okay, so here's that top 500 data. So this is the benchmark for linear systems of equations, right? And now I've just projected out into the future, looking at where we might be. And now if you plot the Bell Prize winners on that, it fits pretty well on that data. So there's some kind of something's going on here. Maybe this Gordon Bell stuff is really just a linear system of equations that they're solving under the covers. But using these machines at scale. Just so you get a picture, the benchmark runs about 75% of peak, 75-80% of peak performance, right? So these applications are running at that rate as well, which is pretty impressive for an application. Our dirty little secret is, for supercomputing, most applications get less than 10% of peak, theoretical peak. And here we've got things which are running really at very high performance rates. And this sort of tells the story that we will get to that exaflop point roughly in 2020, according to this projection. And in a few years we'll be at 10 petaflops and 100 petaflops in the year 2016, if we follow that trend. And, I've got a laptop, and I got to believe that we're going to follow that trend. So where does that put my laptop in a few years? Well, it says, I'm going to have a laptop that's going to be performing at 10 teraflops in that time period. Now, that seems like a joke, and, I have some doubts in my mind if I'll actually have that. But, at some level, exponential things, I got to believe that that's going to happen. And what am I going to do with all that power? Well, what do I do with the power on my machine today? Well, to be honest, it's a great search engine. So I search my laptop for stuff, and I rarely delete anything. And, that power is really coming to use in terms of doing the searching, in terms of being able to find stuff on my machine. So I find it quite useful. And, if I try to use one of my older laptops, I have a hard time because I feel it's so slow compared to what I'm using today. Okay. The top 500 machines. If we take a look at those 500 machines and look at the processors, who's making the processors? Well, Intel is inside 71% of those machines, right? So Intel is a dominant thing. AMD is in 13%, and IBM is in 7% of the machines. So the message here is that commodity processors really are driving high-performance computing. There was a time when specialized machines were part of the high-performance computing scene, specialized vector processors. That time is gone, right? Everything is driven by the commodity processor. The economics of commodity processors really takes over, and the companies can't compete making specialized processors at this level. So commodity is really where things are going. That wasn't supposed to happen. Oh, so this is looking at the number of, so who owns the machines? So the US has 58% of the computers, 58% of the machines. The UK has 9%, France, Germany, 5%, Japan, about 4%, China, and the list goes on. But very dominant U.S. presence in terms of high-performance computing. This is the top 10 machines, okay? So these are the 10 fastest ones. The way to read this is the machine at number 1. It's at a Department of Energy laboratory. It's at Los Alamos National Laboratory. It's called the Roadrunner. It's made by IBM. It's in the US. It has 129,000 core. So think of core as processors, right? That's our new term for processors. And it runs at 1.1 petaflops is the execution speed, and it reached 76% of its theoretical peak, right? So that's the efficiency that it had for running this benchmark. And you can see the other machines down the list here. If we just scan down the list, a few things strike us. US has 8 of the 9 machines. There's 2 machines in Germany, in Jülich at the research facility there. There's a lot of cores in these machines, right? So here's one with close to 300,000 cores in it. And they're reaching about 75 to 90% of the theoretical peak for those machines. And this is the rate of execution. Look at the difference between number 1 and number 2. Very, very small separation. And that was at my place, Oak Ridge. So that was an interesting story behind that. The other thing we scan down the list here, the Department of Energy gets it. They bought into high-performance computing in a big way. So high-performance computing simulation, numerical simulation, is a big part of DOE. So DOE has 2 parts. It has the defense part, and it has the part which does open science. The defense part is done by Los Alamos, Sandia, and Livermore. And the open science part is done by Argonne, Oak Ridge, and Lawrence Berkeley Lab. Right? That's how things strike out. So Los Alamos is defense. Oak Ridge is open science. Livermore is defense. Argonne is open science, and Livermore. So again, a smattering across that list. The National Science Foundation has supercomputer centers, and the University of Tennessee, where we are, has a supercomputer center. It's number 6 on the list. It's a big Cray machine. And also the other UT, University of Texas, is number 8 on that list. Right? The machine at Tennessee is an interesting one. When we wrote the proposal for that, we said we wanted to have a supercomputer center. We gave a number of reasons, and we said if we get this, we're not going to put the machine at the University of Tennessee. We're going to put it at Oak Ridge National Laboratory. University of Tennessee doesn't have the space, it doesn't have the power, doesn't have the networking, doesn't have the security to have this machine, doesn't have the expertise, the people. But we can put that all at Oak Ridge and leverage off of what's at Oak Ridge. Oak Ridge has an enormous computing facility. One of the things that happens with high-performance systems is they require a lot of power, right? So processors today require a lot of power. And the power consumption for these machines is measured in megawatts, right? So, take a look at the numbers here. The machine we have at Oak Ridge is 7 megawatts for that machine. 7 megawatts. That's under load. So what is a megawatt? Megawatt per year is $1 million. 1 megawatt is roughly $1 million. So to turn that machine on for a year, the power bill is about $7 million. And this is going to continue to go up. So these machines are not very green in that sense, right? Not very green at all. But the greenest one here, almost the greenest one, is in fact it is the guy at the number 1 position. So it has the best efficiency, flops per watt. So we're at 400 flops per watt. So we want that number to be as high as possible. And you see it's better than all the other guys there. And one reason is that the processor that's used there for the computation in the Roadrunner is a processor that's used in a game console. It's used in the PlayStation 3, right? It's a similar processor. Slight difference in terms of floating point, but that's really the only difference, and I'll talk about that in just a moment. In Canada, there are 8 systems on the top 500 list, and you have one of those systems here. I don't know if you knew that. So Toronto has a couple. The machine here, which is at position number 163. Western Ontario, there's a couple at IT providers and a couple more at some other places there. So in Canada, high-performance computing is used in the academic setting more than not. This is the Roadrunner. This is the fastest machine, and it's a hybrid system. It's made of AMD dual processor part and a cell processor. So the AMD is a dual core, two processors on the die, and each core gets a cell processor. So if we take a look at that, if we were to say that this is the dual core AMD chip, each core gets a cell chip. Cell chip has a 9-core chip, 9 core. 1 core is a PowerPC architecture, and 8 cores do vector processing. Right? So asymmetric kind of thing going on here. And if you're going to program this machine, you have to write a program for the AMD processor, you have to write a program for the PowerPC, and you have to write a program for the vector processor. So you have to write 3 programs to make this thing work. 3 programs, not 1, 3 times 120,000, right? And that's the applications that the guys at Los Alamos the guys at Los Alamos have made an argument that their applications run very well on this architecture, and you know I don't know specifically what their applications are, but they made the case. So again, this hybrid design is it's going to cause is going to cause a disruption in terms of programming. Here, it's a tour de force, I think, to get applications up on this machine because of those 3 programming models that one has faced with in terms of getting the applications up. Okay, so Moore's law is alive and well. This is looking at the number of transistors or gates on chip going, you know, from 1970 roughly up to today, and that's going up at some rate. You know, think of it doubling every 18 to 24 months. And that's going to continue in the future. The other thing that has been happening is that the frequency has been going up as well. So our architect friends have been putting more gates on the chip, and they've also been enhancing the frequency of those processors until just recently. Enhancing the frequency was a big deal. So, you know, I get a new machine, I'd take my applications from my old machine, put it on the new machine, and it would run faster. I wouldn't have to do anything. The frequency got enhanced, my applications ran faster. I was a happy guy. No more, I didn't have to program anything. I just put the old on the new, and things got better. Today, however, those cores are not increasing the frequency. The frequency is flattened at this point. About 3 gigahertz is the frequency, and that's going to continue for the future, they claim. The number of cores on the chip was flat at 1, and now the number of cores have been increasing. That's increasing because they have to find something to do with those gates, so those gates get turned into cores, and the cores are there. And you know, the other thing that's happened here is that the power consumption of these chips has also been going up, and that's really why they can't continue to increase the frequency of the processors because of the relationship between the frequency and the power consumption. The power consumption is roughly fixed here at 100 watts, right? 100 watts. So today's chips run at roughly 100 watts, and those chips, 100 watts. Think of 100 watts. Think about a 100-watt light bulb, and think about touching that. Think about that now in the space of your fingernail, and think about having to remove the heat associated with that, right? And now think about 100,000 of those things put into a package, right? So you know, the power consumption here is really a big issue. But that fact that our applications are no longer going to be enhanced on our new machines is going to cause a major change in what goes on, because I'm not going to be a happy guy. My application on my new machine is not going to run faster unless I do something, unless I program in parallel, right? The frequency is not changing. My old machine and my new machine is the same frequency. Unless I can use those cores, I'm not going to see the benefit of that enhanced architecture, and that's going to be a big deal. So that hardware issue just became a big software problem, and we have to solve that software problem somehow. Okay, so what? So now my thing stopped working. Okay, so here's the situation that we have today. The power is proportional to the voltage squared times the frequency. That's how CMOS current CMOS works. And with current CMOS, the frequency is proportional to the voltage. So that says that the power goes something like the frequency cubed. So you see the problem. If I double the frequency, the power just goes up by a factor of 8, right? So I can't continue to do that. I can't get things get too hot. You know, we're going to melt. We're going to start stuff on fire at that rate. And you know, we take a look at the architecture. We take a look at the frequency, and if we think about enhancing the frequency, making it rise by 50%, then the power consumption goes to over 3 times for that 50% enhancement in frequency. So what the architects have done is they said, look, we're going to give you multi-core. We're going to give you 2 cores, and we're going to run them slower even. We're going to run them at 75%. And if we run those things at 75%, and if you can use those 2 cores, then your performance is going to be 1.5 times what you had before. And the power is going to be at 0.8. So we end up with a 50% more performance with our dual core and 20% less power. So that's the argument for multi-core. And again, don't think 2s, think 4s. You know, we're up to 8 on our sockets now. So Fujitsu has an 8-core chip, commodity chip. Intel has an 8-core chip. AMD is at a 6-core chip. And those numbers are just going to increase in the future. So Moore's law really needs to be reinterpreted in some sense from the software standpoint. And it's really, you know, we think about doubling the number of transistors, but we really should be thinking about doubling the number of threads of execution every 2 years. If we take a look at the top 500 and take a look at the top 15 machines, and look at the number of cores in those top 15 machines, this is the picture. The number of cores over time in the top 15 machines, we're at about 1.5 million cores tied up in those top 15 machines, right? And that number is going up. And at a log scale, that looks like 100 million cores in the top 15 machines within the next 8 or 9 years. Okay, so major changes in the software are going to be caused because of multi-core. It's a very disruptive technology, right? So we have to rewrite our software. And you know, to be honest, the scientific community gets it. We've been doing parallel processing for a long time, right? Probably not at the scale that we have in front of us, but we understand about parallel processing. This is terrifying the rest of the community, though. The guys who do commercial software, they have to rewrite everything. You know, think about Microsoft. They have to rewrite all their software. Think about MathWorks. They have to rewrite all of their software to take advantage of the new architecture. They didn't have to do that before because the frequency change gave them the boost. Today, the frequency change isn't there. They get the boost because of the multi-core. All of that software has to be rewritten. It's a major deal. And you know, we're looking at this from the standpoint of our numerical libraries. So we've been involved in the design of software for LAPACK and ScalaPack, and all that software is going to change. All that software is changing. And you know, we're figuring out as we go exactly how to do that. But I'll give you some picture as to what's going on. So here's the LU factorization from LAPACK. So this is a code which was written based on doing matrix multiply, doing blocked operations. And on a quad socket, 4 sockets, 4-core board, right? So we've got 16 cores there. The theoretical peak for that system, it's an Intel-based system, is about 150 gigaflops, the theoretical peak. The code from LAPACK, when we run it on this machine, using a good set of underlying BLAs that can take advantage of the threads of execution there, gives us about 40 gigaflops. So this is quite a stunning result. It's a very poor performance that we see on software that in some sense was designed to run on a shared memory machine. This is a shared memory system. The multi-core is changing the performance characteristics of our software. We got much better latency and bandwidth associated with it, and the algorithms that we have are not really designed for dealing with this situation. So what's going on? The LAPACK routine is a block partitioned algorithm. Block partitioned in the sense that at the first step here, we're gonna look at a number of columns and call that a panel and do a factorization of that panel. And that's a very sequentialized operation. After we do that, we can do a matrix multiply. A matrix multiply is something which we can on a bunch of processors. So we do a sequential part of the work, and then we fork off and do a bunch of things in parallel, and then we're going to come back together again and do a join. A very bulk synchronous kind of parallel processing going on here. So that's the first step. We go on to the second step. We carry that on until we consume the matrix. That's the flow of the algorithm. And in a cartoon version, you know, we think about factoring a panel, interchanging something, doing a triangular solve, and doing a matrix multiply. So there's that fork join kind of parallelism. There's the sequentialization part, and that consumes one major step of the algorithm. In terms of a graph, we might think of doing the sequential part and then doing the parallel stuff, doing the sequential part in parallel, and continuing that until we consume the matrix. And if we look at a timing diagram for this, we end up with something going as a single thread of execution and then doing something in parallel, single thread in parallel, and it continues with that flow. So, you know, the way to view this is on a 16-core system. I can engage all the processors for this part of the computation, but here I only engage one processor, and that leads to that very poor performance. So we need to redo that and try to shrink, get rid of that white space, because that's the thing which is causing us to be very inefficient. So we basically want to restructure the algorithm and restructure it in terms of breaking it up into smaller blocks and trying to do as enough work to let us carry on to the next step before we carry on with the rest of the panel factorization. So we have a slightly different algorithm involved in this scheme that we're looking at. It involves smaller tasks, we call them tiles of work, and it allows us to basically unroll or unfold the execution so that we can basically get ahead of ourselves and start work for the next step before we finish the current step that we're on. And if we look at the algorithm, again, in terms of a diagram, we're doing initially a sequential part of the work, and then we do just enough of that parallel part so we can start the next sequential part, and that frees up more parallel work to be done. And we basically build a directed acyclic graph of the computation, sort of unfolding things, letting the computation be more event-driven and allowing us to, in effect, overlap more of the computation, various steps of the computation. And if we take a look at the performance characteristic of that, that basically has squeezed out a large amount of that white space and produces an algorithm which is much more effective on those 16 cores. So we're looking for algorithms which are asynchronous to avoid that bulk synchronous kind of thing, very dynamic in terms of scheduling that work as soon as possible, trying to look at finer grained tasks, and trying to organize the data so it fits with those tiles so the data is ready for execution when the computation is ready to go. So instead of organizing the data in perhaps a column fashion, we're going to organize the data in terms of tiles, where the tile size has been optimized for the computation that we're about to engage in. And the algorithm is going to change. The algorithm is going to change slightly, and we're concerned about the numerics of that algorithm, but the factorization doesn't engage the whole panel, it engages tiles. And the way to think of this is instead of doing the pivot down the whole column, we're going to pivot on a tile basis. The analogy here is with an algorithm for LU that's called pointwise pivoting algorithm. So the style here is we engage, we do a factorization of one block doing partial pivoting, and then we look at two blocks where we use the first block to eliminate the second block and do pivoting within those two blocks. And after that's eliminated, we carry on with the next block. And while this work has been done, we apply that work to the right, and it generates more parallel work to be done. So we're allowed to overlap or to start this asynchronous behavior. And then we eliminate the next step, and then that generates more work, and we carry on that computation. So the execution behavior of this algorithm enhances the performance. This is the old LAPACK algorithm, and this is the algorithm that we're calling plasma. That simple change, or that reorganization, allows us to get an algorithm which is more than a factor of 2 more efficient in terms of performance. It doesn't really do more work, but we're concerned a little bit about the numerical behavior. So this is looking at the backward error. We're looking at the normalized residual for the computation, and we're looking at the number of tiles that we do for various sizes of matrices here. So this is a plot of how the residual is behaving as we change the number of tiles, okay? So this normalized residual, we like to see it less than 1. If it grows larger than 1, then we're going to be losing precision in our solution, more precision than we expect to. And with a tile size of 1, meaning it does regular pivoting, we end up with this scenario in terms of the results. And as we enhance the tile size, we see the residual growing in terms of its size, but it never is greater than 1. So we feel fairly confident. It is backward stable, and we feel that we're justified in using this algorithm. So that's one of the changes that we see for plasma to allow us to break that association. And we're expressing these algorithms in terms of a DAG, a directed acyclic graph. And if we had small matrices, what we would do is generate the DAG ahead of time, figure out the critical path in the DAG, the longest path, execute it, and that would free up the most work to be done in parallel. Okay, unfortunately, we can't generate the DAG ahead of time. These DAGs are enormous. So this is a DAG for a 20 by 20 tiled matrix. So the DAGs are just enormous. So I can't generate the whole DAG. What I have to generate is a window. So our strategy is to generate a window of the DAG, execute it, and as we execute it, unfold that window. We want DAGs to be as wide as possible, right? That generates the most parallel work. A DAG which is a stick is the worst situation, where everything is sequentialized. So DAGs which are very wide present the most opportunity for parallel processing. So again, we have this window. We generate a window of this DAG, we execute it, and then we move the window down, executing as we go along until we consume the matrix. So that's the style. We've built our own scheduler for this. So we've designed an algorithm. We've designed a scheduler that allows us to take the tasks as they're generated and then schedule them for execution on the multi-core system. So we're designing our own little internal execution system for these nodes based on the dependencies they're scheduled for execution. Today's machines are based on commodity processors, but with the occurrence of accelerators, graphical processing units, we see that they're going to be a presence in terms of high-performance computing. So today's systems, Intel's about to introduce an architecture called Larrabee. It's going to have some number of cores. Some of those cores will be commodity cores. Some of those cores will be graphics cores, which we can use for accelerators. AMD has a processor in design called Fusion, again, which is an embedded x86 architecture with graphics capability or floating point capability. And NVIDIA currently has boards which are really attached processors. And I have to believe that somehow they're looking for a strategy which can involve taking some commodity architecture and embedding it within their accelerator to provide something like the Intel or the AMD solution. x86 is controlled by Intel. Somehow AMD got control of it a few years ago, and they're allowed to build machines with that architecture. But at the moment, NVIDIA doesn't have access to that design. So we want to take our algorithms that we have for the standard case and transition them to hybrid systems. And what we think of doing is to use both the multi-core and the graphics component that's on our system. And we have to partition the work so that part of the work is done by the multi-core and part of the work is done by the GPU. And today we're organizing that again around this notion of a DAG, splitting off the computational component, the computationally intense component, and giving that to the GPU, and letting the core follow the flow of execution that's on the critical path. And that allows us to effectively use these graphics units, as I'll show you. But just to start, just to show you the capability of these graphics boards, this is an NVIDIA board, the GXT 2800. The next generation was called Tesla. Tesla and this are very similar. NVIDIA talks about a 240 core board. So they want us to believe it's 240 cores on this attached processor. But the way to really think of it is the cores they're talking about are streaming units, SIMD vector processing like units. And they're organized, 8 of them are organized together to really present one execution model. So instead of thinking of 240 cores, they really have 30 cores in their graphics board. Each one of those cores has 8 SIMD units associated with it. Each one of those units can do the following operations, the floating point components. They can do a mul add, that gives us 2 flops, and they can do a multiply. So they can do 3 floating point operations every cycle. That's what they claim in their Tesla. 3 floating point operations every cycle. Their cycle time is 1.3 gigahertz, so 1.3 times 3 times 240 gives us 933 gigaflops. That's out of a Tesla board, which is very inexpensive compared to a regular system, very inexpensive. But here's the rub from the floating point, from our standpoint. I can't use this multiply. This multiply unit here is not of little use to me. I use this operation here, the mul add. That's a triad operation. A multiply followed by an add, and those are linked together. That extra multiply is wasted. So the peak performance is not this number here. It's really 2/3 of it, right? So in some sense, for numerical algorithms, most of us are going to be only able to think of the theoretical peak as at 624 flops. And that's in single precision, so short precision, 32-bit floating point arithmetic, right? In double precision, it's a different story. It's a factor of 8 less, 8 less. So that number of 624 goes down to 78 gigaflops in 64-bit floating point arithmetic. And then there's a story about how it's connected. It's connected over a very slow link, and that slow link runs at 141 gigabytes per second. So that's the data movement from the commodity processor over to the graphics unit. And this board has 1 gigabyte of memory, so that's going to be another limitation. And then there's some characteristics about what we actually see on the board itself. So that's sort of a reality check apart from the hype that you might hear from NVIDIA. So how does it perform? So we're running our algorithms, the algorithms I just talked about, the core, a single core, and a single GPU board. These are the results that we see. These are for LU, QR, and Cholesky, expressed the way I've described in the previous thing for LU. We're using 1 core and 1 GPU, And the performance we see looks like, it's about 280 gigaflops, in single precision. And in double precision, we get that factor of 8 less in terms of performance, just because of the rates, the rate varying. So there we're seeing something on the order of close to 70 gigaflops for our GPU. Now, that's much better than the single core, of course. The single core performance is at 17 gigaflops and at 8 gigaflops on the commodity processor. So we're seeing much higher performance levels clearly from the GPU. So it does make sense to use that GPU. And this is a project we have called Magma. So we're unfolding our software along that dimension. So we have multi-core and multi-core plus GPU that's about to be unfolded. And this is a QR factorization looking at a single core performance. Again, very, very slow performance relative to the GPU. This is looking at 8 cores, using an 8 cores. This is 1 core, 8 cores, and this is using the single core plus GPU, performance. So you see the difference associated with that performance. And again, these GPUs are relatively low cost in terms of it. So we do have some software available that if you're interested, you could use. It's called Magma, and we have these one-sided factorizations, LU, Cholesky, QR, single and double precision. There's an algorithm that uses iterative refinement, which tries to leverage off the fact that the factorization is done in a short precision, and then using iterative refinement, selectively using double precision, enhance the performance up to the accuracy of full precision. And we're looking at two-sided factorizations for the eigenvalue problem as well. We're also looking at multiple GPUs. So we have a system in place which has 4 Tesla cards attached to a 4-core socket CPU. And what we're trying to do is to give each core an attached processor to deal with in terms of its operations. And again, we're splitting the computation up so that the single core is looking at things on the diagonal, and the GPU is doing basically the bulk of the work, the matrix multiply components, which are specified there. So this is a Cholesky factorization. The basic components are a rank K update, followed by a factorization, followed by a matrix multiply, followed by a triangular solve. And again, each CPU gets a GPU associated with it. We try to offload as much of the work as possible to that GPU, and letting it do its job. So this basically says the same story. And here's the performance that we see on that scenario. So this is a Cholesky factorization. It's in single precision. We have 4 core. It's an Opteron-based, AMD-based processor, and a Tesla, 4 Tesla cards associated with it. This is using 1 core and one GPU, 2 cores and 2, 3 cores and 3, and 4 cores and 4 GPUs. So the performance that we see is, in fact, for single precision results, greater than a teraflop out of that ensemble, certainly for large matrices. The limitation of our software today is the amount of memory associated with the GPU. The matrix sits within the GPU itself and is communicated or passed back to the CPU for certain operations, but that's there. So again, we see very high performance associated with it. Again, it's a situation which looks very promising for the GPUs. In terms of performance and in terms of effectively utilizing that computing environment, this is a timing diagram, if you will, for that algorithm. The white space is where things are idle. We want to minimize the amount of white space within the execution, and we're doing a pretty good job of that, although there are some gaps there that we might want to consider improving. So again, it's a good story. In double precision, again, the performance is decreased by this factor of 8 because of the way floating point is done on these processors, and we see the same effect that we saw before. Things are scaling in a very clean way. So we get this weak scaling ability of our algorithms here. As we increase the size of the problem, the performance is scaling along with that. The other issue is about software and how that software is maintained. So we would like to make as little change as possible going from one environment to the next. So this is a characterization of the Cholesky factorization, doing our operations and doing a factorization within the context of LAPACK. And going to Plasma, we make some minor changes to that code to affect things from one to the other, minimizing the amount of changes that we have to make in our codes. We have to do some initialization to get the scheduler up and running. We call our Plasma factorization routine, and a lot of details are done within there. And then we finalize things or close things down. And going to Magma, we have to be concerned about moving data over to the GPU, doing the computation on the GPU, and then occasionally moving items back to the host side. And similarly, when going to a multiple GPU situation. So we think we have a grasp on how that software could be organized in terms of accommodating this multi-core, multiple accelerator based architecture, and we're proceeding with that design. in the future, we understand things are going to enhance in a very significant way, and we want to be prepared for that. But today's architectures look like they're going to be focused on this kind of an algorithm, kind of hardware structure for the future. DARPA, the Defense Advanced Research Projects Agency, recently took on a study of what it would take to get to exaflop computing. So looking at when we would be at the exaflop point. So what it would take to get there, what it would mean in terms of the architecture that we would have in front of us. And here's sort of a summary of that study. It said that exascale systems are likely in 2017, plus or minus a couple of years. So it'll be feasible to build those systems. Those systems will have between 10 and 100 million cores in them, processing elements in them. 3D packaging will be likely. So today's processors, chips, are designed so that the data comes in from the perimeter, right? So we have a chip sitting on a board, and the pins are on the perimeter of that, and data has to come from memory into that processor through those pins. As we increase the processing power, increase the number of cores that we have, the amount of data that we need to get into that chip is enhanced. So one way that we can accommodate that is by building memory on top of the processor and letting data flow vertically into the processor itself. So Intel and AMD are designing three-dimensional chips which will do just that. So 3D packaging, they claimed, will be available to us in this time frame, and it'll most likely have optical interconnects on the chip, passing data between the cores on the chip, and then additionally optical interconnect between devices within our system itself. The aggregate memory of these systems will be between 10 and 100 petabytes. So that seems like a lot, but the rule of thumb today is 1 byte per flop of your machine. You have a machine which has so many flops, you want 1 byte for each of those flops. So we've got a system here which is an exaflop machine. Based on that rule of thumb, we should have an exabyte of data. But the projection here is that we won't be able to have an exabyte, and there's issues about power and cost associated with it, which are driving things down. So that's going to have an implication on the algorithms that we use on these machines. The algorithms that we want to use have a scaling property, is that we increase the size of the problem, we can get scaling by increasing the number of processors that we use. But here we're going to be limited in terms of the size of the problems that we can run. We're not going to be able to increase them at the same rate. So we'll see some issues result as scaling issues from our algorithms that have to be taken into account. They predict that they'll have hardware and software fault management that'll be able to take care of our system in the presence of failure. We'll have heterogeneous cores, and the power that's going to be required for these systems will be greater than, or be on the order of 10 to 100 megawatts of power required to drive these systems. So incredible power demands associated with that. So power, may be one of the limiting factors in our ability to build these machines, our ability to fire them up, basically. So if you're interested in that study, which is quite interesting in detail, you should go to Google and type exascale computing study, and that would get you a copy of that. Okay, so in conclusion, let me just say a couple of things. For the last decade or so, the research has been driven really by looking at the hardware, looking at the race car in some sense. And in that same sense, we haven't spent enough of our attention on the other components that go into making up our high-performance system. So think of it as an ecosystem, right? So we have hardware, we have operating systems, we have compilers, we have applications, we have algorithms, we have software, and that all goes into making up that ecosystem. And in some sense, we focused on the hardware aspect of it, on the race car and its performance, its peak performance. And we need to spend more effort on looking at other components that go into that scenario. There's no Moore's law for software or for algorithms. Things aren't going to be enhanced in that way, and we need to spend a considerable amount of time and effort in doing the design. And that's especially true of programming languages. The programming model that we have today, is from the 70s. We have a programming model which sits in terms of Fortran and C based on MPI, a very, very terse assembly language for moving around messages. And that really has to change when presented with hundreds of millions of processors and trying to coordinate the execution across that model. Okay, so there you have it. That's my story. So that's the Plasma and Magma project. If you're interested in software, there is software available. This is a joint project with my colleague at Berkeley, Jim Demmel, and a number of people at the University of Tennessee and also at the University of Colorado, Denver. The funding that we receive for the work comes from some traditional places and some places which are perhaps not so traditional. So the National Science Foundation and Department of Energy are sponsors of our work. So we write proposals and get grants from them. NVIDIA has recently made us one of their centers of excellence. And we get funding from Microsoft and also from the MathWorks. These guys are terrified in terms of designing software, right? So MathWorks, they have to rewrite everything, and they don't know how to do it. So they're struggling to do that. So they're looking for help. Microsoft is also, struggling for ideas, maybe not for numerical software, but they're funding projects around the country, around the world actually, to help get a better grip on multicore and how they might effectively use multicore for various applications. If you're interested in finding out, reading more about stuff, you go to my webpage, and the easiest way to go to my webpage is go to Google, type in my name, and click I'm Feeling Lucky, and that'll send you to my webpage. So there you go. I'd be happy to answer any questions you might have. So here's a question. Okay, so you're wondering what's beyond exaflop. Well, it's zettaflop, right? It's a zettaflop. So it's 10 to the 21. 10 to the 21. And then the question is, what's beyond that? So this is sort of amazing to me. They've got it figured out. So there you go. And I don't think I'll be around for lunaflop here, but they've got it all mapped out there for you. It's not as organized as I thought, but that's the list. Yes. Right. So So this is not a very green thing. 100 megawatts is not very green. And what's the story behind that? So some people feel these machines are vital, play a major role in terms of various things, in terms of climate modeling, weather prediction, in terms of the safety of the country, in terms of other things. So they're willing to invest in this to get to that point. It's like, if we're gonna launch a rocket to the moon, that becomes the mission, and the fact that we ignite this incredible device, which is not very green, to get us there is just part of the process that we have to go through to get us to that point. People are talking about devices which are a bit greener for computing, but at this level, I don't see it. I see this is something which is very intensely energy hog, and I don't see any way around it. We do have processors which are very efficient. Intel makes something called the Atom, which is in some netbooks, which is very low power indeed. But in terms of floating point capability, in terms of satisfying the needs of the scientific community at scale, at the top end, that won't effectively make it.
Now, what that leads me to is that
see.
So it seems that you got, whichever way you go with that question, you got hard answers. So which way could you go?
So I think your premise is not correct. I think each of those points, each of those 5 points has algorithms at its core and software. So fault tolerance, we have to design algorithms which are fault tolerant. So that's a job of the algorithm, and the software has to realize that. So that becomes embedded in the algorithm itself. In terms of all of those points, communication avoiding is not trying to reduce the communication. It's trying to reduce the algorithm's structure so that it's not the hardware issue, it's the algorithm issue. So I would say each of those points really deal with an algorithmic aspect. My concern about education is, people are not learning about parallel programming. They're not learning how to do things in parallel. That should be the first course in some sense, is how to do things in parallel. That should be the introduction to things. Everything is parallel now. Everything is parallel. And without that ability to deal with parallel processing, we're going to be handicapped in terms of the hardware and the architectures that are coming. So in some sense, we need to restructure and rethink. And we have not spent enough attention on that problem. It's been there for a long time, and now it's coming front and center in everything that we do, and we're not prepared for it. We don't educate people in the right way to effectively deal with the hardwares that we have, and that's going to be the big issue. So trying to get parallel processing as the first course in programming would make a lot of sense. They're trying to sort out that issue. So it involves, again, parallel. How do you design things at a parallel level? So everything has to be designed that way. We're restructuring. So I don't know how Microsoft's going to do it. I don't have a bullet or an answer for them. Our answer is to try to look at a DAG-based organization for our algorithms and trying to express things so that we can have this asynchronous kind of operations going on within our algorithms, and to design it from the ground up and to allow things to run. We're looking to run things at scale. So we're looking at beyond 100,000 processors here. We have to be our software is intended to run in that configuration. And now Microsoft doesn't have 100,000 perhaps in front of it, but it has some large number of processors in front of it. MathWorks has this problem. I would say they're concerned about their software, about their strategy for moving forward, and they don't have a good strategy today.
I have a question about Magma.
Yeah.
So, sort of different things. One is the GPU memory hierarchy is rapidly changing every iteration of the processor.
Yeah.
How sensitive do you find your work is to change to the specific memory hierarchy of a particular processor? And as a follow-up to that, how do you think you're going to parameterize your work to allow for the rapid evolving?
Yeah, that's a good question. So we don't have any standard here with accelerators. There's no standards in place. We're programming today as if NVIDIA is the thing, and that's not going to happen. I mean, CUDA is not going to be the thing that we have. I'm not sure OpenCL. Yeah, maybe OpenCL might be, but I see this as a time for experimentation. We have to understand what the interactions are between the two components, and design things that work in that space. We're not yet ready. The software we have is not at all at the state of some of the other software we deliver, but we want to give people an opportunity to experiment with it. So this is the time for experimentation, a time where we can give people things and get feedback, and a time to try out ideas. So our interfaces and everything is very tentative. We're not casting anything in concrete. This is not something which is the final answer to our software problems. It's one point in the experimentation. And will it change? Absolutely. And how will it change? I'm not sure yet. I'm not sure that we have exactly the right answer for the current situation. We get pretty good results, right? It's sort of the best results I've seen so far for GPUs, for using the NVIDIA stuff anyway.
And that's going to change, you know, in the next year with Larrabee coming onto the scene. And, you know, beyond that, everything's going to sort of, everything will morph at that point. So nothing is, this is the experimentation time. There's no standards. This is not a time when we can say this is the definite answer to this problem. Yes?
Yeah, one last thing. I've been programming clusters with MPI. I've got some DT280 cards, and I'm trying to do some of the smaller things on that.
Yeah.
And for dense matrices, it's fine. I
Yeah.
get 10 times speed up.
Yeah.
When I'm dealing with sparse matrices,
Yeah.
I just can't get the speed up on
Right.
it. Now, I understand the Fermi chip from NVIDIA is going to have some indirect addressing.
Yeah.
It should have better support for
Right.
sparse
Sparse matrices.
matrices. I think that's going to, you know, so many matrices these days are huge and they're sparse.
Absolutely.
We really need that sparse matrix capability.
Yeah. Yeah. So yeah, Fermi's not here. That's the next generation of the NVIDIA stuff. You know, I see the specs, but I don't see we haven't had an opportunity to test drive one yet. Eventually we will, that's right. But so you're absolutely right that sparse matrices present a different challenge for the design and implementation. They have a different structure. You know, they don't have the luxury of n cubed flops per n squared data references. There's a different balance between them and need to be structured in a different way, and probably can't reach the same levels of performance that we're seeing here in terms of the dense algorithms, right? So things have to be changed in a different way for that case. Our experiments are looking at, you know, what can we do in this situation? So we haven't approached the sparse problems yet, and they're very challenging. And as you say, many problems are formulated in terms of those sparse problems.
Okay, great. So let's thank Jack again for a wonderful job.
And there you have it.
Great. Enjoyed it greatly.
Yes, well, it's a lot of stuff to get through.
Yeah, no. So do you think that MATLAB will give us single precision ever?
They do have single.
Oh, they do? I didn't know that.
So if you there's a function called single,
Yeah.
and so if you were to say bracket LU bracket equals single of LU of A, it would use single precision.
All right, I didn't know that.
And it would so we use LA-PAC, we use a single precision version. If it had those routines, it would actually use them.
Now, do they do, I mean, in the built-in stuff, they also kind of follow your, I don't know, the thing, backslash, if they do iterative design?
No, they don't. So you have to and we, you know, we do it. You have to write a little program.
I see.
But, you know, it's easy to do, and you get it in MATLAB. So if you were to write that code in MATLAB for doing iterative refinement, you would see the factors.
Okay.
And in MATLAB. Yeah, of course. We do it. Good to see you. Where? That's right. Somewhere else. Somewhere around the world. That's right. You have to get your speed up. That's right.
It's about 5 years ago.
I was going to calculate.
Yes, you can.
5 years ago, I was having a conversation with Chuck Packer.
Yeah.
You know, I'd asked him the question, you know, what's Microsoft's biggest feature?
Oh, yeah.
And you know, I was surprised his answer was hypothetical trade condition.
Yeah.
Right? I mean, it was, instead he said, you know, it's the multi-partition. Right? He said that Intel and AMD are shoving it on us. We know exactly why they're doing it. They don't have any dumb. They don't have any.
That's right.
Nobody knows how to run it.
That's right. So, yeah, they're quite aware of it. And they you know.
Oh, he's very, yeah, they're very well.
And you know, Craig Mundy, who is a friend, you know, he's yeah, these guys
It
know.
was interesting because he asked me, he said, you know, he said, if you would teach your students how to do parallel programming, you'd hire everyone in your guys.
I see.
And my response to him was, we don't know how to do it either.
I see. Yes, that's
And
right.
he said, that doesn't matter. He says, teach them what you do. Learn some basic algorithms, learn where the overheads are, or some very lightweight formal methods so that they know how to diagnose races and how to check these. So that would put them ahead of anything else. finally got our first undergraduate course in parallel programming, not on the calendar yet, but last year because you know, still viewed as too hard.
It's viewed as too hard.
It's viewed as too hard, right? You know, and when I came back, I said, you know, because I just got told by Microsoft that we've got basic parallel programming into our curriculum, they'd hire every one of our graduates. Actually, said that they would try, but they couldn't because, of course, there's too many people.
Yeah.
But the real challenge is overcoming this barrier. It's just too hard.
But it's
Right?
provoking right here, yeah.
Yeah.
Good to see you. That's right. That's right. Good to see you. That's right. Enjoy it. That's right. That's right. Take care. Take care. That's right.
Yeah, thanks. So, have a good
Yeah, you bet. Yes, my long drive back.
Yeah,
As it were.
going down.
Going back. Excellent.
Very good.
So,
That was great.
so
Really
good. I'm
very
glad you
nice.
enjoyed it. Yes.
Oh, yeah, yeah.
This wireless thing doesn't work very well here.
Oh, it's
So-
not working again?
So, well, I'm not sure. So let's see what we have here. Oh, it is working. It is working. My mail was screwed up then.
Okay, so can you
So
check your email? Yeah.
I'm just trying here to suck it in, but it'll take a few minutes now.
Yeah.
So, you know, I had this trouble with the wireless in your building. It didn't, wouldn't let me in. I get an IP address. It was DNS, it was able to resolve DNS, but it couldn't ping out. It was like I wasn't connected. So I had,
Actually, the ping thing, I'm not entirely surprised, but
Yeah.
it may be logging pings.
Hey, Bill. How are you?
so, and then wired it worked.
Wired work.
Yeah, no problem. So I don't understand that.
Well, we've got different subnets with different subscribers
Yeah,
also.
yeah.
So, I mean, for example, apparently Mark's ISD got a huge DNS attack over the last week.
Did they?
6 machines were being attacked for that. Instead of login, brute force login with password. And so they
But our IT guys got it.
Jack, this is Bill, our chair.
Bill, how you doing? Nice
Hi,
to see you.
Jack.
Good to see you. That's
Pleasure.
right. Good to see you.
Pleasure.
That's
Thank
right.
you so much for
Well,
coming.
it was
Great
my
talk.
pleasure. Yeah, it was good. It was fun.
Yeah, lots of great days.
Yeah, overwhelming
I
almost.
like
But
the
that's
yeah.
that's right. Yes, it's coming. It's coming.
Yeah.
So how does your laptop compare to flops per watt?
You know, I haven't done the flops per watt. It's pretty good though. So it's about what, 30 watts. This machine. So it does pretty good. Those watts, by the way, were just the watts for the. I should have showed that other picture. It's the watts just for the processor, memory, and interconnect. It doesn't include the watts for the all the other air conditioning and stuff. That's right. Yeah, that's right.
Spaces.
Yeah, so it's enormous. That's another 50%, I think.
Well, like, the one thing I just noticed is that the i7 laptops are out now, and they're like a couple $100 cheaper than the equivalent on the old quad
It's
cores.
all right.
And one of the reasons is because you only got 2 chips to worry about. You
I
don't
see.
have that Northbridge, which is 20 watts.
I see.
You got the Southbridge basically in the CPU. So there's less heat, and the chips are a little more efficient in the thing. So
Yeah.
the actual prices dropped just overnight, like $200
Wow.
on these quad core laptops.
Yeah, yeah.
Since you're running a Mac, maybe you know, I forgot the name of it. So Mac has this for distributing work among the cores for multi-threading.
Yeah.
It's what's it called? It's like Grand Central Dispatch.
Yeah,
Grand
so
Central Dispatch.
I don't know much
Have you
about
looked
that.
at
No, I haven't looked at it, no,
Because
in detail.
they also, just like in the last month, open sourced a portion of
I
it.
see.
And, you know, I'm sure it's basically some kind of consumer producer
Yes, arrangement, that's right,
arrangement.
yeah.
But in terms of, you know, at least for a commodity thing like this, as opposed to, you know, high performance
That's right,
computing, where
that's
you
right.
really care about, you know, every flop.
Yes,
You know, well, time will tell. But,
That's right.
But for a machine like this, where it's got lots of different kinds of work to do,
that's right.
it's not clear how much you really have to parallelize, right? I mean, as
Right.
long as there's kind of a lot of different kinds of things to do, and you have this consumer producer
That's right.
thing happening.
It's probably okay. So a machine like
You know,
this,
probably not up to 1,000 cores, but.
that's right.
You know,
That's right. That's right. So Intel is working on something as well, and I know Microsoft has some ideas about how they want to do their scheduling of tasks
Yeah.
also. And those are still, you know, in development, let's say, but I'll take a look at them.
Yeah, I'll take a look. I mean, it might, you know, again, it's sort of more like a
Yeah.
consumer play.
That's
It's
right.
never going to be for, you know, super
core will keep switching between the cores.
Oh, yeah.
And they've, with the i7 cores where they can boost it, but other cores are idle, they can boost the frequency.
They get the
That,
frequency up.
if you start shifting, then that loses that. So the algorithm in Windows 7 now doesn't, it works closer with the CPU in terms of determining when it's going to switch to a different core.
I see.
Just sort of trying to optimize it a little bit better.
Yeah.
So that's certainly getting more and more.
Sky's the limit.
Yeah, absolutely.
Well, the problem is that
Good to see you. That's right. That's right. Good to see you.
Yeah,
That's right.
no,
Yeah, I had a fun time. You have quite a good scientific computing group.
Yeah, no,
They have a core of. They have a good core.
no, it's great. It's fantastic. And, yeah, so at Tennessee, do they have, there's a traditional problem about
Where you sit.
applied math or
Yeah,
computer
we're
science.
in the CS equivalent. We're in EECS.
Okay.
So there's some guys in math department as well, but there's about 4 or 5 of us who claim to do scientific computing in the department, and we're not the major players, not the we're not the dominant group, but they tolerate us.
Yeah.